Hey there. So we're going to be doing Chapter 8 today, and that's oxidation and reduction that we're going to be looking at. Now, one of the things you want to keep in mind for this chapter is this is kind of a duality, if you will. We have oxidation, and that always has to happen alongside reduction. And this is why typically these are actually referred to as redox, as one word. And that's because when you look at this, you can take the first part here. So this is the second part right there. And that gives you redox. And they're always a duality. If you have an oxidation, you have to have a reduction. If you have a reduction, you have to have something that was oxidized as well. Okay, and so this right here is your learning objectives for this, which I always like to have in there. This is going to be at first. You'll see that there's actually a lot of places around you where redox reactions are occurring all the time. And so, for example, you breathing right now as you watch this video, that is a redox reaction in and of itself. And so you're experiencing redox reactions with every breath you take. This is a more colorful, interesting redox reaction. As you can see, it's typically referred to as the volcano reaction because it makes a nice little volcano effect. And specifically, this is going to be the ammonium dichromate reaction. I would not recommend doing this yourselves, by the way. The end products for this is a form of chromium, specifically a dichromate here that's made down here. And that's actually quite toxic. It's one of the places, if you've ever heard of like Tamil Nadu or you heard of Aaron Brockovich, that's hexachromium. It's extremely toxic, very, very bad for the people, environment, everything. And so you have to be really careful about disposing of this reaction. But there are wonderful videos that I can go ahead and show you a cool example of this reaction. With fancy music behind it. And right there you're seeing a reduction and oxidation occurring. And so hopefully you guys see that. It's beautiful. And it is very beautiful. Also makes a hell of a mess. And this is all that chromium, by the way. That sort of greenish powder down here. That's all that hexachromium, the dichromate over here. The gas being evolved is this N2 here, which is this really kind of nasty, which is the same gas that would be in the atmosphere, right there, N2. And then we have water being evolved, which is actually vapor. You can kind of see the vapor, but not really, because it's in the gaseous form. But the dichromate is the green stuff that's all over the screen now. They put it quite a bit. Okay, so this right here is a sort of summary, a nice summary of your oxidation reductions. When you have an oxidation, typical guidelines that sort of guide you and say, hey, an oxidation occurred here, is that you gain an oxygen. So if you go to products and you've gained an oxygen, you'll see over here, we got more oxygens for hydrogen over on the right side, on the left side. Man, they really like putting ads in those links now. Then gaining an oxygen, this is a hallmark of an oxidation. If we lose an oxygen, this is a hallmark of a reduction. That's something that has been reduced. Losing a hydrogen, this is a mark of an oxidation again. If we lose electrons, that's an oxidation as well. Or we increase the oxidation number. I haven't really talked about the oxidation number, but it's an easy way to track this loss or gain of electrons, or another way of saying that, easy way of tracking the oxidation state, how oxidized something is. Over here we have reduction, and that's gaining hydrogen, losing an oxygen again, gaining an electron. This is the easy way I actually find to remember this process, is that when we're reduced, when we have a reduction happen, we gain a negative thing, which is electrons. And so reduction is gaining electrons, negative things, i.e. literally reducing the number. Or we decrease the oxidation number. Oxidation numbers are actually just methods of tracking numbers of electrons. So if you have an additional electron, you're going to have a negative oxidation number. If you have less electrons than you would normally have because of your number of protons, remember, typically protons and electrons are equal. So if you lose an electron, your oxidation number is going to go up. And this is kind of the easy way I think is usually the easiest to remember oxidation, is that in an oxidation, your oxidation number goes up. Another way of saying that is you lose an electron. Okay, there is a mnemonic. Okay, I'm going to give you the mnemonic. In my experience, the number of people that actually remember oxidation reduction from this mnemonic is actually very low. I've had much, much better luck with reduction means gaining a negative thing, which is an electron. But the mnemonic goes, Leo the lion goes grr. And you really play it up, and you'll maybe remember it better. Leo the lion goes grrr. I tried. I have a bit of a cough today, so that grr did not turn out as well as I would have preferred. Leo is LEO, loss of electrons is oxidation. Grr is gain of electrons is reduction. Now, in my experience, everybody remembers Leo the lion goes grr, and then they forget what it means. Which, oh well, I guess. Just whatever method you use to remember it, this is the overall thing you need to remember. And these are all related back to each other. And like if you gain electrons, then hydrogens don't hold on to electrons very well, and so gaining hydrogens is the same as gaining electrons. Oxygen is one of the most electronegative elements on the periodic table, and so gaining oxygens means that you're losing electrons. The oxygens are taking them from you. And again, the oxidation number is just a count of number of electrons as opposed to the number of protons. Okay, so this right here is another oxidation reduction. You're all probably quite familiar with this one because this one's combustion. We're taking methane, which is one of the major components of natural gas. That's usually about somewhere between 60 and 80 something percent of natural gas, depending on where you get the natural gas from. We're then burning it in the presence of oxygen, and that's producing CO2 and water. And that's your typical combustion reaction. And that always has been an oxidation reduction reaction as well, or a redox reaction. I'm probably going to say redox reaction from now on. It's what I typically do. But if I say redox reaction, please remember that it's oxidation reduction reaction, redox reaction. They mean the same thing. There's no difference. It's fine either way. Okay? Okay, so we need to talk about oxidizing and reducing agents. Okay. So if I say a secret agent stole government information, then they aren't the information. The secret agent isn't the one being stolen, right? And this is one of those things that people have a lot of trouble with for some reason. And it's that oxidizing agents is like saying assassinating agent. The agent's not the one that died. And so an oxidizing agent causes an oxidation. A reducing agent causes a reduction. Just like an assassinating agent doesn't get killed, they kill someone. And so be very careful. Try to keep this straight in your head. It's very common for students to mistake oxidizing agents and think the agent is the one that gets oxidized. And for some reason, it just trips people up. Remember that oxidizing agents are the ones that cause the oxidation. Whatever it's with is the thing that gets oxidized. Okay? And so the oxidizing agent itself is the one that actually gets reduced. It's the one that takes the electrons from something. And so oxidizing agents take electrons away from something. Reducing agents, on the other hand, give electrons to things. Okay, and so this right here is a demonstration of oxidation reduction in terms of the oxidation number. Now, the oxidation number is just the comparison of protons and electrons on any given atom. And so an oxidation number of 0 says that we have equal amounts. If we're oxidized from there, we could go to +1, in which case we have lost an electron. Now we have one additional proton than electron. If we go up to +2, then we're going to have lost 2 electrons. We have 2 more protons than we have electrons, which gives us a +2 charge. Notice that these are actually, when we looked at the Mg2+, K+, things like that, these are actually oxidation numbers here. Those were actually oxidation numbers that entire time. So like Mg here has a 2+ oxidation number, or 2+ charge. So whenever we were looking on our monoatomics, where we just had one atom, this oxidation number is actually the same as the charge. It's only when we have stuff that's more complicated that the oxidation number becomes very important, because the charge is not so obvious. Let's go ahead and look at some more examples, though. It's a bit more interesting to look at examples. So I actually have a pair of glasses like this on me right now. And these are photochromic lenses. You can get them in your glasses where they'll change color when you're outside, so that they're a little bit more shaded. And so this is photochromic chromic lenses. What they have is they have silver and copper chloride that are embedded in the glass. And so when they're not in the presence of sunlight, or actually UV, which is what actually triggers it, and basically all these glasses, you can make ones that are not UV triggered, but I don't think anybody does that. What you'll get is clear. See, it's clear. It's not really shaded any. And, that's good, because you don't want them to be shaded heavily when you're inside. Now, when you're in the presence of UV radiation, i.e. sunlight, what's going to happen is the silver ions are actually going to be reduced. These are going to form clusters of silver atoms that will then darken the lenses. And so that's what you're seeing right here. See how they're very much darker now? And that's because we've actually had the UV radiation perform a reduction, in this case, of silver. The silver metal is opaque. It actually blocks a fair amount of the sunlight. And that's what you're seeing here. And you can see it's actually quite a bit of blockage. They're pretty effective photochromic lenses in this case. Mine don't really work that well. I'm a little jealous now. So right here we actually have the beginnings of what we're going to talk about in terms of electrochemical cells and batteries. So we have oxidation reduction reactions. These can produce electricity. This is an example of an oxidation reduction reaction again. This one is not specifically for an electrochemical cell that would actually produce energy, but we'll get into those in just a bit. This one's just a really nice demonstration visually of this. And that's because what we have here is we have a copper metal wire, and we have the colorless silver ions that are in solution. So we have like a silver nitrate in solution. And so if you put this copper in and leave it for a while, it does take a bit, though you can speed this up with electricity and a variety of other ways. What will happen is the copper will actually dissolve in solution, and that makes the solution blue. That's actually like copper nitrate makes solutions blue. And you see how the wire is getting like jagged and kind of fuzzy looking, right? And the reason that's happening is the silver metal is actually depositing out as silver solid metal onto that copper wire. It doesn't deposit it nice and evenly like was over here, because that was actually cast and then stretched out into wire. whereas this is just randomly deposited out wherever it happens to land. And so it ends up looking kind of messy in comparison. You could take that metal and remelt it down, and then you'd have nice silver metal. Though you would probably have a little bit of copper left in there, because it won't be perfect. Though you can get very pure reactions when you do a nice electroplating. That's actually like nickel plating and platinum plating that you probably have heard about. It's a very similar process that we're doing right here. Chemical electrical plating is what we're doing right now. Technically, we're silver plating this copper wire, which is a bit of a waste, but we're doing it. So electrodes, these are going to be pieces of metal where the electrons are going to be transferred. Anodes are going to be electrodes where the oxidation occurs. Cathodes are going to be electrodes where the reduction occurs. One of the kind of easy ways to help you out here is that reductions is where you gain electrons. Cations are positive things that would want to take electrons. And so the cathode is going to take cations and put electrons on them for reduction. Anodes, on the other hand, are going to be where your electrodes have the oxidation occurs. It's where they're going to take the electrons from something. Anions have electrons to take, and so you take electrons from anions at an anode. Okay? And that's kind of how I remember this when I try to remember these things. Remember that what we're going to be looking at is we're going to be looking at a reduction and an oxidation reaction. In the case of an electrochemical cells, we're going to take these two reactions and we're physically going to break them up somehow so that we can actually separate them and not have them happen all over the place where we can't actually take anything from it and use it. And we're going to take these two reactions, we're going to connect them with a wire. And these wire, well, of course, the stuff that's not in the reaction is just wire. That's just where electricity is passing. But the part that's in here, okay, where the oxidation occurs, that is your anode. And the part here where the reduction occurs, that is going to be your cathode. And so we're quite literally going to spatially break these things apart. Isn't that nice? Normally our reactions, we're breaking these things apart in our minds. But no, we're going to physically break them apart this time. So the oxidation reduction reactions, these can be represented by half reactions. And so this would be the different halves of the reactions, because in many of these cases, we can break these apart. And the reason we can break these apart is because we can actually pass electrons through wires. And so we literally can physically break many of these reactions apart. You can do them in a single reaction too. This is actually us doing it in a single tube rather than breaking it apart. On the other hand, this is the overall reaction. So notice that in oxidation, you lose electrons. And so electrons are in your products. In reduction, we gain electrons. And so the electrons are in our reactants. Overall, this reaction would look like this. Note that we have on the left side these things right here, right? So copper solid plus Ag plus right there. Note, however, because the electrons are on the right side over here and the left side here, when we add those two reactions together, we're going to cancel them. And so we'll actually negate the overall transfer of electrons in this overall reaction. Or another way of saying that is we're actually representing that transfer of electrons with these right here. See how that goes from positive to 0. And so that actually told us a transfer of electrons occurred in the overall reaction. Note our products here are just down here like this, and those are our products. And so we just added those together, same way you might take two equations in math and you just add them together. And anything that shows up on both sides would end up canceling. Because these are ultimately equations, just like you see in math. Excuse me for clearing my throat and stuff. I'm having a lot of trouble with my lungs. Okay, and so this right here is a demonstration of the physical separation of an anode and a cathode. Here we've taken that reaction we showed before in a single test tube. We physically separated it using this porous partition right here. That's this barrier right here in yellow. It's porous, so it can exchange nitrates between the two. And this is going to keep a charge from building up on either side. And so over here we have our anode. And this is going to be where we have our copper metal. And copper metal is going to be going from copper 2 plus right there. And what's going to happen is electrons are going to come up here. They're going to go into a light bulb to show us they're doing something. And that's going to cause light to light. Now, when we're talking about electricity, many people probably did not realize this, but electricity is actually just flowing electrons doing work. Okay? So when you have electrical current going through a wire, all that is we're moving electrons from one side of the wire to the other. And that's just electrical current right there. And amps is actually, if you ever heard volts and amps, volts is that potential, right? And it's the potential of that wire, i.e. it's like saying I have this high of a waterfall, and that's going to drive electrons moving down it. On the other hand, amps is actually the amount of moving electricity. That's the number of electrons that are moving, is what that directly correlates to. Anyways, so what we're having here is we're having moving electrons that are going to move from the anode over to the cathode. And those are just like those electrons that were in the reactant and in the product, right? So these electrons right here in the product, they're being given off over here. Over here, we have our electrons that would be in the reactant. They're going to be used with Ag+ to produce silver metal. And so this process is going to continuously move electrons from one side to the other, over and over and over, and that's going to cause your light bulb here to light. Now, yes, if you thought, hey, that looks like a battery, it is a battery. This is a super expensive, very, very, very bad idea to actually try to use it to power stuff because super expensive. We're using silver here and copper, both pretty expensive metals. But yes, this is a battery, and so you could generate power using this battery. Interestingly enough, we can actually run these the opposite direction too, and we'll talk about that in just a bit. But right here, this is what's referred to as a dry cell. You might notice this looks a lot like the alkaline batteries that you can buy from the like grocery store, or you could buy from Walmart. And that's because this is one example of the alkaline batteries. The alkaline batteries literally their name coming from the base that's used in them. You'll notice this is a hydroxide over here. Literally, it's basic. Okay, and so what we have here is we have two shells and then a graphite rod. And so we have our two cells that are being separated here by this porous spacer right here, which is this blue part. And then we have the zinc case, that's going to be our anode. And then we have a moist paste of MnO2, NH4Cl, and graphite powder. That's this stuff right here, this red stuff. It's not actually red and blue when you actually open these batteries up, by the way, but you get the idea. And right here we have the graphite rod. This is actually just going to act as our cathode. Literally, it's something on-reactive that we can move electrons through, because this moist paste doesn't have a nice wire we could use. Or another way of saying this is this up here doesn't have two sides where one of them is like a nice metal we could use as the cathode. And so that has a bit of a problem there. And so what happens is when you plug these two together, that's going to complete this going over here to the zinc metal case. And that's going to give a pathway for electrons to move through. And as that pathway is completed, what's going to happen is this reaction is going to move forwards. And we're going to move electrons through the wire that you've completed the pathway through. And that'll power devices like your remote. for your streaming TV, whatever, your smart TV, Fire Stick, Google TV, Apple TV, whatever you have, or whatever device you hook up to a battery, right? Okay. And so that right there is what's typically called a dry cell. This is opposed to what's normally called a wet cell. By the next one is actually a wet cell. So that's your like alkaline batteries that you see at the grocery store. One of the most common batteries you see. Um, this right here is your lead storage batteries. This is actually a wet cell. And so it actually has aqueous H2SO4. Yes, that is sulfuric acid, as you may remember from previous material. If you're imagining, oh my goodness, that sounds horribly dangerous. Yes, it is. It is actually incredibly dangerous. Um, Not as dangerous anymore. So this is the lead storage batteries that you'd see in not such great solar panel setups. The better solar panel setups typically have lithium-ion storage batteries, but you can also do the storage batteries as lead storage batteries. Or your car. Your car more is the most likely one that has a lead storage battery. If you don't have an electric car, of course. Electric cars also have lithium-ion batteries. And so what we'll see here is we'll have the lead storage batteries. We again are going to have a redox cells. In this case, they're actually separated as different wafers, and these are the wafers right here. They look a bit like waffles or something, right? And so you have alternating wafers. One is a lead, and that's the anode. That's the blue one here. And then the PbO2 right here is the cathode. And so what you're having here is, again, we have separated anode and cathode, separated oxidation reduction reactions. And so when we complete this wire here, if this has already been recharged, what you're going to have is a discharge of electrons from your anode coming off, and then they'll come onto the cathode over here. And this is going to drive this reaction forward. So we'll have lead going to lead sulfate, which is in the solution. And so the solution gets more lead in it over here. Okay, and so let's say that now you got your car running, crank, 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 crank. We did our discharge, got our car running. Our car's alternator, that's what does that, is now taking some of that energy from our engine running, and it's charging the battery back up. And running a bunch of other stuff probably because we want to listen to music. Okay, and so now we're going to go ahead and put electricity going the reverse direction. So what we're going to do is we're going to pull electrons from our cathode, what used to be our cathode, and we're going to put them onto what used to be our anode. And we're going to drive this reaction in the opposite direction. And so we're going to forcefully take electrons from the PbO2 cathode. We're going to layer the PbSO4 that's in solution back out as lead, solid lead, and lead oxide back out on to these wafers and build those back up. And so we're running this reaction in reverse so that we can store that electricity back into our battery here. Okay, and we're rewinding that reaction. And that's going to build up the amount of materials that we'd have on the reactance side over here. And then when we need it to be discharged again, it'll have more materials to break down and produce electricity later. And so that's actually a rechargeable battery. It's referred to as wet because it has water in it right there. These do dry out over time, by the way. Not as much anymore. They're much better built now. And so usually people just get rid of them when they dry out. It used to be that you used to have to pull the tops off these things and you'd refill them with water. You take like literally a little bottle of water and refill your battery. And if that sounds horribly dangerous and like it's just a recipe for disaster, it really kind of was. So if you messed up on these back in the day, you would boil off all your water. You'd end up with a bunch of solid sitting, sulfuric acid sitting there and lead dust. And then people would like on a hot summer day try to pour water into this thing. It would puff up into their face and melt part of their face off. These things used to be like horribly dangerous. Um, just a better building with they have like a nice mat on them now on the bottom. So what they have is like a gel on the bottom that keeps some of the water in there and makes it sure it never dries out. And they're much better built, so they leak less, the water escapes less, and they have a bit of extra water in that surface down there. And so rarely do you see anything happen where they actually die from that within a decade or so. They're much better now. They really have improved those tremendously. You do see some issues though when you start seeing these things used for like solar panel setups, and yeah, in large amounts. So, anyways, I think that probably nobody's probably interested anymore in that. Now I'm gonna kind of dodge the bullet on lithium-ion batteries. If anybody actually wants to see lithium-ion batteries and talk about lithium-ion batteries, we could put it in, but they're a bit more complex and they don't really make as much sense in terms of a redox reaction without understanding some stuff that we just don't have time to get into in this class. But I can talk about lithium-ion batteries, but it'll have to be kind of abstract. Nickel cadmium batteries, these are actually used still even now, but they were used heavily in portable radios, cordless appliances. What you have is cadmium anodes and nickel oxide cathodes. Um, you can still find nickel cadmium batteries. They're not that uncommon. But a lot of the things that they used to be used for have been replaced with lithium ion batteries, actually. Fuel cells are actually a kind of battery. They're a redox battery, but you can actually continuously add fuel to them instead of having to recharge the fuel that's already there in them. And so the fuel is going to be oxidized at your cathode. The O2 is then reduced at the anode. Uh, excuse me. Yeah, at the anode. And the electrons are going to be allowed to flow through wire and do the work. And what you can do is just instead of having it where the cathode anode are in a jar and they're immobile, what you do is you just continuously put more fuel through and pull the old used fill out, and then you can process that fuel one way or another. The thing you've probably heard before is a like hydrogen fuel cell. Those are really popular in news and reporting and stuff. But there's actually gasoline fuel cells. There's methane fuel cells. There's ethanol fuel cells. There's all sorts of fuel cells. These are actually a lot more ubiquitous and common than people think. They're pretty high technology though, as compared to the traditional combustion engine. And part of the problem with them is electricity has not always been the most usable thing for every single case. The other part of the problem is these require much more detailed tolerances and much more control of the reaction that's happening. They can be very efficient though compared to a combustion engine. Rusting of iron is probably the example of a redox reaction that you are most used to. If I had to guess, this is the one that you've almost for sure seen. And so what you see here is we have a piece of iron, in this case probably a steel, nice steel tool, okay? And so what's happening here is we got a little bit of water. Typically it has a little of ions in it, like salts, and so we have NaCl here. There's our NaCl in our water. And so what we're going to see is this steel here is largely made out of iron. That iron is going to go ahead and lose its electrons, and that's going to give us Fe2+. And notice the iron has now been oxidized. Those electrons are going to go along the metal, which is conductive, and they're going to go to the surface of that water bead. And what they're going to do is they're then going to react with the oxygen. Um, Now, most books actually do something that's a little bit wrong, and they would just go O2. And your book's actually really, really good. I do appreciate this as an environmental chemist, but the major component that's typically used is actually hydroxide. Free radical hydroxide, or OH minus, is what you're actually going to see here. And so you're going to gain this electron onto the oxygen, and then this is going to produce OH minus, and then this is going to react with the Fe2 plus here, which comes to the surface, and that produces the rust right there. And so what we see here is actually the components of rust right there. It's a several stage reaction. Your book's quite complete about this, and it really does a nice job. So that right there is actually the rust. Now you'll see something kind of interesting about this. In this diagram, notice that the rusting does not occur in the water, does it? It takes iron out in the water. Sure, the iron stops being solid that can support a structure in the water, sure. But the rust actually gets produced up on the surface of the water. So if you go to a dock nearby and you see those iron pillars that are standing out of the water, or if you go to a nice bridge with some iron pillars standing out of the water and they've been there for a while, what you'll see is you can actually tell where the water levels normally are because there'll be bands of rust right where the water surface would be. And that's what we're seeing here actually. Now, structurally speaking, the part that's been degraded is the stuff below the water. That's the part that's had the irons actually removed from it, and structurally is probably much weaker than it used to be. But anyways, so that right there is rusting of iron, which is pretty awesome. Now, aluminum is actually more reactive than iron. It's a way, way more reactive. You can actually prove this to yourself a little bit. If you were to take an aluminum piece of aluminum, aluminum can, whatever, and you were to go ahead and scratch that aluminum, if you've ever scratched your piece of aluminum before, or aluminum bottle opener or camp stool or whatever, what you would see is that it's actually that area. And that shininess, and that shininess is actually the actual aluminum. So aluminum is actually very shiny. That dull surface that you probably are thinking of when you're thinking of aluminum is actually the rusted form of aluminum. It's the oxidized form. That's aluminum oxide. Um, and so what's happening whenever you're looking at aluminum objects around you, you're actually seeing the results of their oxidation. That aluminum oxide is extremely hard and unreactive. And so it actually blocks the oxidation of the rest of aluminum by forming on the surface, i.e. that aluminum oxide protects the aluminum from being further oxidized. Now, interestingly enough, you can actually dissolve the aluminum oxide by using mercury. And so if you ever go to an airport, the planes are all made out of aluminum materials, right? And so they have a lot of aluminum in them, and they're very concerned with their aluminum being oxidized, thus structurally impairing the plane, and the plane, developing a hole in it or falling apart or a variety of other things that we don't want to think about. And so when you're looking at this, that mercury, the reason you can't bring mercury on a plane, the reason that there's signs as you go into the airport all say no mercury this, no mercury that, no the old flash bulb, the old timey movies where they go boom, and it's a big flash. Those were all mercury things. And so if you take mercury, it dissolves the aluminum oxide off of the aluminum, and it'll make the aluminum rust really, really fast. And so if you were to accidentally spill a pretty decent amount, I mean, it would have to probably be like a liter of mercury or something. This wouldn't be very easy to do with like a small container of mercury. But if you were to spill a mercury on a plane, it would actually rust through the hull of the plane and make a pretty decent little rusted out section of the plane that could break. So, kind of an interesting thing. Hopefully, nobody ever actually experiences anything like that. Though you can take a bit of mercury and rust out a piece of aluminum if you ever want to see. It's not something that's that bad for the environment or you. Silver tarnish. So everybody's probably seen silver, either a set of silverware or maybe some silver jewelry that's older. And you'll see that there's like this black sort of gunk that develops in the silver. This is referred to as silver tarnish. It's the result of oxide at the silver surface reacting with hydrogen sulfide. Hydrogen sulfide is actually in the air. It's released by a few different sources, but you can have like hydrogen sulfide being released by you in the form of a fart. I know, I had to pick that one. So this is going to leave a black film of silver sulfide. This is Ag2S. And right here we actually see some silver tarnish right there. Right there. And down here we've cleaned the silver tarnish, by the way. So when we polish the tarnish, silver will actually restore the shine. But what's going to happen is we're actually polishing off the silver that's been reacted with the sulfide. And so that silver sulfide right here, or sulfide, excuse me, excuse me, that silver sulfide, when we're polishing that off, we actually do lose all that silver. And so an alternative is to allow aluminum to reduce the silver in the presence of a solution of sodium bicarbonate electrolyte. This will replate the silver out, though to be fair, if you replate the silver out, it does not always plate exactly where you would want it to. So you may still lose some definition. You at least won't lose the silver, I guess. You can recast the silver into something else someday when you've completely lost everything that's meaningful about it. But on the positive side, you got your silver. Let's talk a bit about explosive reactions. Many of the reactions that you think of as, oh wow, that's an explosion. These are actually chemical explosions that are the result of redox reactions. And so the redox reactions that occur rapidly with the production of gases, usually nitrogen is one of the more common examples, these are oftentimes explosive. And the reason they're explosive is that they actually distribute the fuel themselves. And so when they produce the gas, they'll push outwards because the gas will expand. They'll then move the next time the fuel actually triggers a reaction outwards, and they'll keep doing that over and over really, really, really fast. Okay? And so this right here is ANFO. That's ammonium nitrate fuel oil. This is the reaction right here. And I have a little short that I'm going to show here, and hopefully the video works well. And that's
ANFO, ammonia nitrate fuel oil. Strong enough to blow up a mountain, but pH balanced to flip a car.
Okay, I forgot that comment wasn't there. That's true. Funny too. You'll notice that it actually produces nitrogen gas, CO2 gas, and H2O gas. H2O and nitrogen, absolutely no harm to the environment at all. CO2, one of the least harmful gases we can release into the environment, though releasing lots and lots of CO2 in the environment obviously has been shown to have some pretty negative effects. But anyways, now you got to see a car blown up by a ANFO, your nice ammonium nitrate fuel oil explosion. And so, great example of redox reaction. Very, very, very fast, very rapidly expanding, redox reaction. Okay, let's talk a bit about oxygen. Oxygen is probably well, on Earth, oxygen is the most common oxidizing agent. It makes up about 20%, a little bit over 20% of the air, about 50% of the Earth by mass. In the atmosphere, it can exist as several different forms. Probably the forms that are going to be most important to you are going to be oxygen molecules, which is O2, and ozone, which is O3. Most people have heard of ozone before, though they may not know what it looks like and they may not know what it actually does at all. But it's kind of a shame that so few people have kind of heard of what ozone is and why it's important, because it's actually probably, other than O2, which we breathe, it's definitely the most important form of oxygen on the planet, and it's one of the most important things for you to know. And it's actually a case of actual great environmental legislation that worked, which is a shame people don't realize this stuff and know this stuff. So, oxygen reacts with many things. It reacts with metals and nonmetals, forming different oxides. This is why so much of the planet is the Earth's mass is actually oxygen, is because it reacts tremendously with the different metals and nonmetals to form various different minerals. And so there's massive numbers of carbonates, which is a form of oxygen-containing mineral, and just a large amount of the planet that's made up of those then. You, of course, use oxygen by breathing it in, and you use that to produce energy by using up fuel in the form of things like carbohydrates, fats, lipids, of course, and proteins. This right here is ozone. So again, ozone is going to be another powerful oxidizing agent. In the lower atmosphere, it's actually very harmful to both plants and animals. Typically in the lower atmosphere, it's generated by, well, nowadays, the majority of ozone in the lower atmosphere is likely generated in a city, usually due to anthropogenic, i.e. human sources. But it's also generated by things like lightning, and every now and then ozone falls out of the atmosphere down into the lower atmosphere, and so it is harmful to plants and animals, highly oxidizing, highly reactive. However, in the stratosphere, it actually protects life on Earth from harmful ultraviolet radiation. There's actually three forms of UV radiation, i.e. UV light that you may have, gives you a tan normally, or sunburn. We have the lowest energy UV radiation that actually hits the surface of the planet. The higher energy UV radiations are actually so high energy that if you were exposed to high energy UV radiation, you would die in like 15 minutes. You'd be sunburned within a minute. It'd be almost immediately that you'd have sunburn. So even plants can't survive, and bacteria can't survive high energy UV radiation. Okay, so this right here is the what's typically referred to as like the ozone layer or the ozone shield sometimes. And what you can see is this is actually a graphic that is not playing. I broke my graphic. Okay, well, I broke my graphic. Sorry about that. What you would have seen is that after 1979, this is right here what's referred to as the ozone hole. Okay, and what happened is that we released chemicals, largely CFCs, that actually depleted this ozone layer and created a larger and larger ozone hole. And we were actually on track that we would have caused the ozone layer to be depleted and no longer function. And once it would stop functioning, we would have killed all life on the planet, down to about a meter or two into the ocean, and of course any life that was inside caves. And so we almost drove this planet to extinction once before. And like nobody knows about it. And the reason nobody knows about it is after about 2000, we actually have started seeing the ozone layer recover, though we've had a little bit of blockage since then. So we were almost completely recovered as of 2020, And then we started having some political instabilities happen. And so the reason we had this recovered is there was something called the Montreal Accord. It's the only time in the history of the entire world that we have done an environmental alliance where we have actually successfully reversed what was happening that we didn't like. And we did it, and we actually reversed the breakdown of the ozone layer. The ozone layer almost completely recovered. Lately, it has fallen back a little bit, but not badly. It's doing pretty well so far. And that was actually because of um, uh, I'm not going to go too far into it. It has to do with some really, really bad decisions made by the United States and Europe on how they're going to pay companies to destroy materials that would deplete the ozone layer. And then they didn't really think that through very well. And so companies in very poor countries made materials that would deplete the ozone layer to destroy them and make money from this. And then when they stopped paying out as much, they released a lot of these materials, and they've had to kind of like keep paying out on it, or else they'll release the rest of them, and it's a bit of a mess. Anyways, the rest of the Montreal Protocol actually Accords was quite excellent, and they've replaced the majority of the materials that used to do this. Um, so we've actually really it's amazing. If you ever want to see a very successful example of environmental legislation, that would be the one to look at. Only one I can think of that actually worked. Okay, so the hydrogen peroxide, this is another form of oxygen. This is a common oxidizing agent. You may have used it on your wounds before. Um, Typically used as a disinfectant or to bleach hair, literally because those are two things that happen when you oxidize things. So bleaching is a very common oxidizing reaction product, something that happens due to an oxidation reaction. And disinfectant is literally we're oxidizing um, the different bacteria and viruses that might get into your wound and killing them before they have a chance to do anything. That's actually what it does to your iron in your wound too. That's why it foams up like that. You're seeing an oxidation reaction happening. There's some other common oxidizing agents, the less common in your life, except chlorine, just very common in your life, far more common than you probably think. Potassium dichromate. This will oxidize alcohols and turns green when reduced to chromium 3. It's commonly used in breathalyzers, and so this is one of the most common ways that they actually do breathalyzers, and they detect the level of alcohol in your blood. Benzoyl peroxide, it's an antiseptic, and it's used to treat acne as well. Yeah, hit or miss whether you've ever used that, in my experience, but very common acne treatment. Though there are some other acne treatments that seem to work a lot better than that now. Chlorine, used as a disinfectant in the treatment of drinking and wastewater. Now, chlorine is used a lot in small towns. So if you live in a smaller town, you've probably drank chlorine-treated water. It's very cheap compared to the other ways you can treat water on small scales. Now, larger cities don't use chlorine as much because they can get away with using things like UV light or other disinfectant methods like ozone. Um, and those are a lot cheaper once they scale up to really large facilities. But chlorine is definitely the way to go and the most used one when you're talking about small scale facilities like in a small town. So bleaches. These are some different forms of bleach. Bleach is really, really a catch-all of a oxygen chlorine containing compounds that's used as an oxidizing agent typically on a fabric. Bleaches is a wide category of things as compared to most other substances that we would label a single word like that. But overall, these are two different types of bleaches. And these are oxidizing agents that are going to be used on fabrics. Typically, what they're used for is to whiten those fabrics. Interestingly enough, if you're ever wondering how you would traditionally whiten and bleach things before, was you would actually leave them out in a stream that's going over rocks. And that would actually produce free radical hydroxide. So a hydroxide that does not have a negative charge, but instead has an unpaired electron. And that actually also bleaches things. It's actually the most common oxidizing agent when you're talking about just nature in general, because it's much more reactive than oxygen itself, O2. And so this is actually a lot of the oxidation in nature is free radical hydroxide. It's kind of interesting. So metallurgy, reducing agents. We can use coke as a reducing agent. This is actually one of the forms of carbon, one of the many forms of carbon. It's produced by heating coal to draw off the volatile compounds. It's then used as a reducing agent in things like smelting metals. Right here we actually see smelting tin to produce tin. And so here we have one of the forms of tin that you can get, SnO2, that has the oxides right now, so you don't have the metal. You need to reduce it down to the solid metal. So we take it, we heat it with coke. This is going to drive off CO2 and produce tin. Uh, yes, in case you're wondering, smelting metals is a very, very CO2 intensive task and quite energy and expensive as well. Aluminum. This is used to reduce chromium oxide to chromium metal. And so here we actually see chromium oxide. We take aluminum with that. This is going to give us aluminum oxide, and we have chromium. Um, you actually get the aluminum from another reduction, in case you're wondering. Very, very energy intensive as well, though. This is the reduction in photography. I'm Okay, so I left this in here, and I will probably keep doing stuff with photography things, but sometimes somebody's going to have to give me some feedback of whether this actually makes sense to keep photography in here, because I don't think anybody's touched an actual film camera in a while. I heard that they're a little bit back in popularity, but yeah, I'm actually kind of curious if any of you have actually seen a film-based photography system. So, so there's something called photography paper. And this is black and white photography paper. Contains a coating of silver bromide, and that's AgBr. The silver ions that are exposed to light will actually react with the developer, which is hydroquinone. And that's this right here. This forms metallic silver. This is actually, if you've ever seen like a dark room where they develop photographs, this is what they're doing. So the silver ions, not exposed, are going to be removed using a solution of sodium thiosulfate. This produces a negative where the metallic silver is then going to be deposited. And so this is actually what this I'm talking about, these silver ions. So this is the black and white film right here. So the silver ions and the silver bromide in black and white film are going to be exposed to light. They're going to be reduced to black silver metal that then is going to produce a negative image that you can then use to then project and print out onto your photograph that you take. Or you can actually take this and you can actually shine light through it and play it. This is actually why it's called the silver screen, in case you're ever wondering, at the theater, is because it's due to the silver in the film. Yeah. I don't even know if that's helpful to people anymore, though. Anyways, sometimes somebody's gonna have to tell me if that's actually useful and if that makes any sense at all. Because, yeah, I kind of wonder now, how many of you all have actually seen film anything? Like, is that still a thing that people have seen that are below the age of like 30 somethings? Because, man, it went digital completely now. um, you've all probably heard of antioxidants before. Yes, the oxidant is the same oxidant as in oxidation reduction. So these are actually reducing agents that are in food. The most common one you've probably heard of and would be the most relevant to you would probably be vitamin C, which is ascorbic acid. Uh, Tocopherol, which is vitamin E, and vitamin A. These are all antioxidants. And you've probably heard of antioxidants in terms of like anti-aging sort of things, like help you not age. So these are some different reducing agents of interest. Hydrogen as a reducing agent, of course. We have hydrogen, which is excellent agent for reducing both metal and non-metal reagents. This is why one of the hallmarks of being reduced is actually gaining hydrogens. So hydrogen can reduce metallic oxides to their metals, and we actually see an example here. You have a metallic oxide, we put it in with hydrogen gas, this gives us that metal right there, and H2O, which is water. Hydrogens can also reduce double bonds to single bonds. You may have heard of this as hydrogenation. And so if you're looking at peanut butter, what they do with peanut butter is they actually take something that would be a liquid at room temperature. They take that, they put hydrogen through it and do a reaction with the catalyst, which we'll talk about in just a bit. That's called hydrogenation. This makes it so the peanut butter goes liquid a few degrees higher. And so what ends up happening is instead of being a liquid at room temperature, it starts becoming liquidy when you put it on something hot, like a piece of toast. And that gives a nice, beautiful, buttery feeling when it's on toast. And so you get peanut butter, right? Which I think many, many people like. One of the more popular foods that the United States has produced. Nickel or platinum is used as a catalyst for this reaction. Catalysts are going to increase the rate of a chemical reaction by lowering the activation energy. They'll make the reaction go faster in both directions, and they only make the reaction go faster. They don't make the reaction go forward or reverse. They just make it go faster. So, hydrogen is going to be the most abundant element in the universe. It's an important element on Earth. It's seldom found in free state on Earth, however, because we just have too many things to react with it. The majority is actually combined with oxygen, and we'll find it in the form of water. So hydrogen is going to be used in the manufacture of ammonia and methanol. It's also used to hydrogenate vegetable oils, of course. We can make margarines, we can make shortenings, and if we really want to get fancy, we can make peanut butter, which is definitely my favorite of those ones. Yeah. So hydrogen gas, this can be prepared via a number of different ways, actually, but probably the easiest way to get your hands on would be to take zinc and react with hydrochloric acid. You can also take a hydrolysis and use electricity to produce hydrogen gas. If you ever wanted to do that, it's actually kind of like a popular hobby where people generate hydrogen gas for a variety of reasons. You can actually get hydrogen gas generators now too pretty easily. They use them for like emergency responses and stuff. So the oxidation and reduction reactions are going to be critical to life on Earth. Energy is obtained from food via an oxidizing the food. One example is the oxidation of glucose, of course. This pairs very nicely with the photosynthesis of glucose. So we take glucose, we oxidize it. This is partially done. All the oxygen part of this is done in our mitochondria. If you've ever heard of what mitochondria is, the powerhouse of the cell. This is going to produce CO2, water, and energy. We breathe out the CO2, and we use the energy by doing things like lecturing you guys or studying chemistry. No other possible reasons. The only thing you could ever use energy for is valid things like studying for chemistry, of course. Um, the reactions of photosynthesis are going to be a series of reductions. These are going to be the reverse of this reaction above. And so you can see it's basically this just in reverse. So we take CO2 from the atmosphere in a photosynthetic environment. I use something like a plant that does photosynthesis. So we take CO2 from the environment, we take H2O from the environment, we take energy in the form of light from the environment. And those are then going to be combined and used to synthesize sugar, typically glucose, and water, or O2, excuse me. The O2 is typically released out, and that's what then us humans breathe, and we go, thank you, plant. Thank you very much. Again, photosynthesis is going to be one of the most important processes on Earth. As a human, I should probably say the most important process on Earth, because without it, I don't get to breathe, and that would be a problem for me. I enjoy breathing and living. So, these are actually just some nice plant videos showing some plants growing. I
So,
figured I'd do
what
that
are
to
you gonna
finish
ask
this
the
off.
wizard for, Pixel?
Well, I'm not sure he's such a...
Oh, I want him to give me
the commercials this time.
all the magical AI.
And so very relaxing. Then we see the light plus moisture plus some additional minerals so it can make its photosynthetic
Wake up,
enzymes
honey, I
callus.
made you breakfast.
Then we get our
Fresh
plant
coffee
growing,
and
growing,
bagels
producing
too.
sugars to
A
make
new
cellulose.
day is waiting
further
for us. We got lots of fun
And
stuff to do. Let's go to the zoo
Remember, it
and
evolves
feed the
that
monkeys.
oxygen that
I
holds
can
on.
lend them your baseball cap.
So,
Let's make the
as a
day
sort of
a
finish
bit
up,
of fun.
let me say,
Growing up is just a
if you have any
trap.
questions, please let me know.
Don't it seem
Hopefully I covered a
like
pretty good selection of the materials that you could want
like
to learn
putting
about
all
redox
of your
reactions.
joy in
I
a
would be
big brown
interested if
bag.
anybody would
I
see more
won't
complex
listen
material,
to
which would be
any
a
of
lithium-ion
that
battery.
jazz.
Though it
No,
would be
I'll
kind of
never
useful to
grow up.
understand lithium-ion batteries.
Growing up is
One of
just
the
a
things
bit
I will
fat
mention
trap. I take pride in
is
never
that
working a
lithium-ion
day.
batteries,
Can't
the
see the
reason that
use
they
of
light
it
on fire and
anyway.
explode
Who
when you
can think of such a load of
charge them
crap?
properly or charge them when they're too cold
Growing
or
up
hot
is just a trap.
is actually a reduction reaction making lithium metal, which is actually quite flammable. Anyways, I'll probably leave it off here. You all have a wonderful end of the semester, and let me know if there's any questions or you would like any other information. You take care now.